Swayam Prabha. Digital India. Educated India.
Welcome to the 19th lecture of Mechanics of Materials. In the last lecture, we derived the governing equations for a beam bending problem. The equation that we derived was minus sigma xx by y minus y naught equal to mz by izz equal to E by r, which is E d square delta y by dx square, where r is the radius of curvature. And then we also saw in the last but previous lecture that dmg by dx plus vy has to be 0, dvy plus by dx plus qy has to be 0. Combining these two equations, we obtain the equation d square mg by dx square equal to qy by dx square equal to qy, and we combine all these equations to obtain a governing equation in terms of the applied loading qy and the unknown displacement delta y of x. Okay, unknown displacement delta y of x. Okay. Now, let us apply this problem, apply these equations to solve some problems. The first problem that I am going to look at is a simply supported beam, okay, subjected to a uniformly distributed load. A uniformly distributed load W, which can be, this same problem can be represented in one dimensional form as the following. Many of you would be familiar with this. This is of magnitude W. What this support tells us is this is a hinge support. So, delta y, if I measure my coordinate system from here, say this is x, this is y, and this is z, and this length is L. Then what this hinge support says is at x equal to 0, delta y has to be 0, it is free to rotate, since it is simply supported it can rotate freely, okay, but it can't resist any stresses, since there is no continuity at the hinged end, it can't resist any stresses, okay. So, basically that being a hinge, it will resist the vertical deflection, it will resist the horizontal deflection, and hence there will be the traction that is acting on that T's of Ex should be Fx Ex plus integrated this over the area dA would be f of x Ex plus f of y Ey. There is no shear coming on the other direction. So, there will be the traction that is acting on that surface. Similarly, this being a roller end, delta y at x equal to L has to be 0, and the traction that is acting on this end E of x dAx would be just, this will be f b of y Ey, okay. Say this is A and this is B, okay. So, that will be the boundary condition that we are going to apply, okay. Now, let us go about solving this problem. I will use a one dimensional approximation from now on. I have this UDL distributed over a length L, okay. So, I have the equation d square m z by dx square is equal to qy, which in this case, since the load is acting vertically downwards, it will be minus w, okay. Now, then if I integrate it twice, I will get mz to be minus w x square by 2 plus C1x plus C2. Okay. Now, let us look at x equal to L, and there is no horizontal force that is developed at x equal to L n, there is no horizontal force that is developed, and hence since sigma xx has to be 0 because of no continuity or no provision for horizontal stress to develop, you will find that since sigma xx at x equal to L has to be 0, mz which is integral sigma xx into y dAx, Ax has to be 0 at mz at x equal to L. Okay. Now, let us look at this end, hinged end, there is no horizontal force applied throughout in the problem. So, Fx has to be 0 and there is no continuity of the member at the A end again. Since there is no continuity of the member at the A end, there is nothing to support an axial stress sigma xx. If I cut there, I have exposed sigma xx, there is nothing on the other side sigma xx is 0, the support does not provide that sigma xx, and hence at this end also mz at x equal to 0 has to be 0, since again sigma xx at x equal to 0 end is 0. Okay. So, I use this condition that mz at x equal to 0 is C2, and since this is 0, C2 has to be 0, and then I use the condition that mz at x equal to L has to be C1 L minus W L square by 2 has to be 0. From here I get C1 to be W L by 2. Okay. Hence, mz moment as a function of x is given by W by 2 into L x minus x square. Okay. Now, from the governing equations again, once I know my moment, I can estimate the shear force Vy from this equation, which I will do next. So, Vy is minus dmz by dx, which is minus W by 2 L minus 2x. Okay. So, that is Vy of x. Okay. Now, I am interested in finding where bending moment mz max occurs where is the question. To maximize a function, I have to set the derivative to 0. The maximum or minimum of a function will occur where the derivative of the function goes to 0, and hence Vy equal to 0 is L minus 2x, and that will be x is L by 2, this L by 2. So, maximum mz max will occur where mz is at x equal to L by 2, and that will be W L square by 8. Okay. That will be L square by 8, that is the maximum bending moment, and this shows that shear force is 0 when maximum extreme bending moment occurs. Bending moment occurs. Okay. So, let us now first plot these things on this figure, that is I am drawing the shear force and bending moment diagrams. Okay. The bending moment diagram is a parabolic equation. Okay. Its maximum at L by 2, and at x equal to 0 and x equal to L it is 0. So, I know that it is 0 here, 0 here, and then its maximum at L by 2. Now, the question is on which side I have to plot. Okay. Usually you take the positive bending moment to be plotted on the top and negative bending moment to be plotted at the bottom, but we will follow the convention that the bending moment diagram, the line will coincide with the line where the tension occurs. Okay. The beam bends like this, you can see that the top surface is in compression and the bottom surface is in tension, because the length at the bottom has to increase, length at the top has to decrease for it to, when it curves like this. Okay. Hence what happens is the tension occurs at the bottom, so we will plot the positive bending moment at the bottom and negative bending moments at the top. Okay. So at L by 2 you have W L square by 8, this occurs at L by 2. Okay. Now it is a parabolic equation, so it is not a linear equation, so I join this like this. It becomes a parabolic curve like that. Okay. Now let us plot the shear force. Let us plot the shear force. This is the bending moment diagram. What I am plotting now is the shear force diagram. Okay. What happens for the shear force at x equal to 0? From here Vy at 0 is minus WL by 2 and Vy at x equal to L is WL by 2. Okay. Now what is the meaning of this? The shear force has a sign which corresponds to the sign of the shear stress. Okay. So we will plot it with the sign as such, and shear force at L by 2 is 0. So the shear force variation would be something like this, it is a linear curve. Okay. So it is negative here, positive here, this is a positive bending moment WL by 2 and that is WL by 2. Let us understand why this is negative and this is positive. Okay. So if I take a section here, negative shear, the positive shear force should act like this. This is the positive shear force. This negative meaning it is acting upward there, which is right because I am applying a downward force. So the resultant will be an upward acting force. On this face, this is a positive shear and the reaction forces are acting upward there. Okay. So that is why the sign of the shear force changes from the left end to the right end. Okay. What it means is, from force equilibrium you can see that this reaction force should be W into L by 2 and this reaction force should be W into L by 2, both acting vertically upwards. Since the beam is symmetric, we expect the reaction forces to be symmetric, same. Okay. Now we have found the bending moment and shear forces. Next let us find the stresses and displacements. Okay.